So today we're going to be factoring. What we're going to start factoring with is we're going to start with 4-term polynomials. And if we remember, factoring from Algebra 1 is reversing distribution, which means we are going to, instead of taking, in this example, 2 binomials and either foiling or distributing them together, we're going to undo that process. Now, this is a skill that we're going to use a lot when we're reducing complicated functions to graph either rational equations or when finding limits, because we can take something that is very, very complicated and reduce it down to something that's very easy to look at and easy to use. So let's go ahead and get started with this. Now, when we factor, what we're doing today is factoring by grouping, which means I'm going to group my left 2 terms and my right 2 terms. I put parentheses around them to differentiate. This is one group and this is another group. But I can't just put parentheses because that would change addition to multiplication. So what is always implied with this is that there's always a plus sign between the 2 groups. That way we don't change the operations. And then what I do is I go ahead and I pull out my greatest common factor. Because again, if we're distributing something in, to undo that, we're going to factor something out. So we're going to pull out our greatest common factor out of both of these. In the GCF of 6 and 24, the largest number I can divide both of them by is 6. The largest number I can divide both of these by is 2. And now, also we notice there's no equal sign over here, which means I can't just go ahead and divide this by 6. I can't just divide this by 2. I'm actually multiplying and dividing by 2. So what I've done is I've said, hey, 2 divided by 2, and I've scooched that 2 over there. So now this 2 doesn't exist. But I have multiplied and divided by the same thing. Doing the same thing over here. After I multiply and divide by 6, I'm going to scooch that over, and then this will no longer exist. And some of you noticed that not only can I divide by a 2 and a 6, but over here they both share an x value. 2 x values to be exact. I have 2 on the right and 3 on the left. I can divide at most 2 out of both of them, which means that actually what I've done is I've multiplied and divided by a 6x squared. I've just scooched that over. So now the only thing left up top is my 6x squared. The only thing left up top is my plus 2. And after I divide and I simplify what's in these equations, so 24 divided by 6 gives me 4. I took away 2 of the x's. Negative 6 divided by 6 is 1. I took away all the x's. 8 divided by 2 is 4. Negative 2 divided by 2 is 1. Okay. And so what we notice right here is we notice yet again I have another GCF. Remember, binomials, I'm going to have to do this twice. So I'm pulled out a GCF, and I'm going to pull out another GCF. So I'm going to go ahead, and I'm going to divide by in this case, a 4x minus 1. But remember, I can't just go ahead and divide an expression by something. I have to multiply and divide by the same thing so it doesn't change. I'm just going to scooch that over. 4x minus 1, so that we know this no longer exists. I notice right here I have a 4x minus 1 up in both those terms, which means that cancels out. Now all that I'm left with is the original numerator of the fraction, which is a 6x squared plus 2. So in this case I have a 6x squared plus 2. And my second term is a 4x minus 1. And boom, there is my final answer. Now, this is a lot of double writing, and it seems unnecessary, but what I wanted to show, at least in this first example, of how we can change the appearance of this polynomial into a set of 2 binomials. Now, we can also factor out an additional 2. We're not necessarily worried about that. We just wanted to factor this by grouping. But I wanted to show you that I'm not just dividing. I'm not doing arbitrary operations to an expression because that mathematically cannot be done. But I can multiply by 1 or divide by 1. I can add 0 or subtract 0. I can do things of that nature. And that's exactly what we're going to do. If we multiply by 1, it doesn't matter how the 1 looks, but if I multiply by part of it being a GCF, it'll help us walk through this. So let's do it again. See if it doesn't clear some things up. So what we're going to do is we are going to group this. Then when I group it, I'm going to divide out the GCF and say, okay, I'm dividing in this case by a 2y squared. And over here, there is no GCF by a 1. And a lot of you are noticing that I'm not dividing by a -1. We're going to explain how to do that in just a moment. So if I pull out my 2y squared, all that I'm left with is 2y plus 1. Because remember, I still have a 2y squared up top. I still have a 1 up top. So that way it's times 1 times 1. I still have a plus sign between the two, which means this is plus 1, parenthesis, negative 2y minus 1. And what we notice here is what a lot of you have already noticed. Hey, I have the same two terms, but the wrong signs. I have a positive 2y, a negative 2y, positive 1, and negative 1. And so one of the rules that we tend to follow is if I have a leading negative coefficient, I just go ahead and pull out a negative 1. And what that'll do is that always ensures that my leading coefficient is positive because my other leading coefficient is generally assumed to be positive. And it makes this step a single step as opposed to what we're going to have to do. And we're going to have to do it a second time. Divide by -1, remember times -1, so that we can get a 2y plus 1, 2y plus 1. And now that negative is up in the numerator, that becomes a -1. This stays at 2y squared. Boom. Now we have something that we can work with. So I have my original numerator. I am going to multiply and divide by a 2y plus 1, 2y plus 1. And so because I multiplied and divided, I can cancel these out, which leaves me with my first term of a 2y squared minus 1 and a second term of 2y plus 1. Boom. And there is our answer. So the rule is generally negative leading coefficient, factor out a negative in the first step. It'll save you some time. Now, some of you might be asking, hey, what happens if I don't spot the greatest common factor on the first go? What happens if I didn't see a 6? What happened if I did a 3? Well, let's take a look at what will happen with this one. So if I go ahead and I factor out what I'm attempting to be a greatest common factor, but might not, at least in this case. Let's say instead of noticing that these are divisible by 4, let's say we only notice the 2. And I have a y squared, and we get everything else right. I divide out a 2y squared, I divide out a 3, which remember, we know there's still a 3, we know there's a 2y squared up top. What we notice is that I have a 2y squared, I have a 2y plus 4. I add my 3, and I have a y plus 2. We notice that our expression here, we want these to be the same. I have a y plus 2 and I have 2y plus 4. They're not. So sometimes we think that we might be doing it wrong, but in this case, we notice that 2 and 4 still have a common factor. What's the common factor? 2. So I'm going to pull out an additional 2, which means that what I should have pulled out originally, if I pull out an additional 2, should have pulled out a 4 originally. But that's okay because we don't need to get the greatest common factor on the first go. It just makes it to where we write less. It reduces the amount of steps. So we have a 4y squared. That's a plus 3 if you believe it. And I have a y plus 2. I have a y plus 2. And so what we're going to do here is I'm going to box this up and say, hey, I'm going to divide by a y plus 2, but in order to keep it balanced, I'm also going to multiply by a y plus 2. And I notice that right here, they cancel out, so I'm left with a y plus 2 and a 4y squared plus 3. And that is our final answer. So again, we don't need to notice everything right up front, but if we notice we need to change signs, pull out a negative. If we notice that we didn't fully divide out the greatest common factor, we just do it again. And we move the new factor out with the other one. So this is a very flexible method, which is one of the reasons why we show it. So with this one, let's walk through this one really quickly. What we're going to do is we're going to pull out our greatest common factor of 6x squared and 5. We remember there's a 5 and a 6x squared. What I'm going to do is I'm going to show a slightly faster way to write this. Instead of writing out every little piece, I get a 6x squared and a plus of 5. And I have an 11x minus 6, 11x minus 6. Now, instead of writing out the times and divide, what a lot of people do, and this is still technically correct, but you're kind of skipping a step here, is they'll jump all the way to the very end. And they'll say, hey, I noticed that one of my factors is going to be an 11x minus 6, and the other factor is going to be 6x squared plus 5. Well, and that is our answer. So, do we always need to write every single little piece? Not necessarily, as long as you know that these are the same terms. And so we're going to end this on what happens when we try and factor something like this. Now, most of us, we'd look at this and say, hey, I'm going to group this. And so we'd group it, and we'd say, okay, I can pull out a 3, and I can pull out a z. So that means I have a 3, I have a z cubed minus 2, I have my z, and I have a 2 minus 9z. And you're like, wait, they aren't the same. Okay, this can't be factored by grouping. And sometimes you might be right, but in this case, do you notice how this one, the terms aren't in alphanumeric order? That might help you out. Oftentimes, if one grouping method doesn't work, you can rewrite the problem, group it a different way, and have it work. So let's try that. Let's instead list this in alphanumeric order, which means we list the biggest term by power and work our way down, which means first, second, third, and fourth term. Let's see what we get. 3z cubed minus 9z squared plus 2z minus 6. Let's try and factor by grouping in this order. A lot of you might be saying, well, does order really matter when it comes to a polynomial? Well, in this case it does. So if we pull out our GCFs, 3z squared and a 2, it means I have a 3z squared plus 2. If I divide out 3, so I get a z minus 3. Here, I get a z minus 3. So I know one of my terms is going to be a z minus 3 because I get the same factors. And I get a 3z squared plus 2. And boom. So albeit the first group didn't work, we rewrote it in alphanumeric order, and all of a sudden we got it to work. So today we're going to be factoring polynomials, specifically quadratics, that only have 3 terms. And the way we're going to do this is we're going to break this middle term into 2 separate terms. This is going to allow us to pull out that GCF out of each piece, which is going to result in that binomial. Now, when we make the list, we're going to call it a list of composite factors, because we know that when we distribute, let's say I have, for example, an x plus 2 and an x minus 3. I know the 2 and the 3 multiplied together are going to get me a negative 6. So whatever two numbers we get right here are going to have to multiply together to get me my C term. But I know my 2x and my negative 3x are going to combine to make this B term. So I'm looking for factors of 18 that make a sum or a difference of 9. And so let's take a look. If I'm looking for factors of 18, a positive 18 I might add, that make a sum or difference of 9, well, I'm going to start with my most common factor of 1 and 18. I'm going to go up to 2, 3, 4 doesn't work, 5 doesn't work, 6 is repeating itself. Once we repeat ourselves, we do what I call completing the loop. Those are all the whole number factors that we're going to list. Can this work with decimals? Yes. Can it work with irrational numbers? Yes. For this method, we're only going to use the whole number factors. So when I have those, I notice that I have a positive 18, which means I'm going to sum these numbers because the only way I can multiply to get a positive number is either a negative negative or a positive positive. I cannot multiply anything else other than the same sign. So if these are the same sign, I'll get a 19, I'll get an 11, and I'll get a 9. So now you tell me which two factors of 18 multiply to get 18 and add up to 9. Well, it's got to be 3 and 6. And so that's exactly what we're going to do. X squared plus 18 is I'm going to break that 9x into a 3x and a 6x, which we know that with a 3 and a 6, those would combine to make our 9, but this allows us to factor this by grouping. So what we'll do is we'll say, okay, let's group the first two and the second two and pull out our GCFs. We have a GCF here of x, we have a GCF here of positive 6, which means if I have my x and my positive 6, my remaining portions of the factor are going to be an x plus 3 and an x plus 3. Now what this means is that with these two terms, I must have distributed an x to get these two. I must have distributed a 6 to get these two. So therefore, that must be one of my binomials. If I distributed an x and a 6 into something, and that something is the same something, that means those are my two factors. Those are the two binomials that when we distribute will get me this. Let's try another one, just to make sure we're good on this. So again, I'm looking for factors of 21 that add up to 4. So if I have a 21, I have 1 and 21, and 3 and 7. 2 doesn't work, 4 doesn't work, 5 doesn't work, 6 doesn't work, 7, and we have completed the loop. Now, this time I noticed that my 21 is a negative number, which means the only way I can multiply to get a negative is if one of these is a positive and one of these is a negative. So let's do that. Let's make this the difference. So the difference between 21 and 1 is going to be 20. You notice how we didn't add them together, but we subtracted them? Again, because they have to have different signs. And a 4. So then I look, what two numbers multiply to give me 21 and make a difference of 4? Well, 3 and 7. So I'm going to break, well, actually this time it's a y. I'm going to break my middle term into a 7y and a 3y. And here's the question, how do I make a positive 4? Well, I can either take 7 minus 3 or 3 minus 7, as long as they have different signs. And the only way we can get a positive 4 is if I add the 7 and subtract the 3. This will allow me to group and pull out my GCF. I have a y and a GCF of negative 3. Remember, we tend to pull out negative coefficients or negative factors if we have a leading negative coefficient, which leaves me with a y minus 3. I'm left with a y plus 7, y plus 7. And because I notice I must have distributed this into the y plus 7 and this into the y plus 7, that means that both the y and the minus 3 must be right up against the y plus 7. And those are the two factors. Now, this seems pretty straightforward, and the fun part about this, it doesn't matter which order you put them in. You can put the 3 first or the 6 first. It doesn't matter. The only difference you'll see in your answer is I'll pull out the x plus 6. If I put the 6 first, I would have pulled out the x plus 3 first. So you notice how my GCF is one of the terms? Well, if I flipped them, my GCF would have been the other term. So it really doesn't matter which way you put them, as long as you make sure you get the signs right. Let's try one more. This time, I have a leading coefficient of 2, which means I'm not just going to go off my factors of 10. I have to also go off my factors of 2. And I'm going to combine those. So 2 times 10 is going to get me a positive 20. And I'm going to list all factors of positive 20, and we'll see why here in a moment. So if I go 1 and 20, 2 and 10, 4 and 5, and I have completed my loop. I notice that this is a positive, which means I'm going to be adding these. Whatever they are, they're either both going to be positive or they're both going to be negative. We don't really care. Here, I get 21, 12, and 9. Looks like the only ones that sum up to make my 9 are a 4 and a 5. So I'm going to say, okay, plus 4x plus 5x. Now again, we can work this whichever way we like. I could put the 5 first or the 4 first. If you work it out, you will get the same answer as what we're about to do right now. Now here, I notice that I'm going to pull out a GCF of 2x, which is different than my first two, where I just pulled out a variable. This is because one of these two factors has to have a 2, because the only way that when I FOIL these, if I FOIL these, I get a y squared. If I FOIL these, I get an x squared. The only way that when I FOIL them to get a 2x squared is that one of them has to have a 2. And lo and behold, we pulled out the 2 right here. So after I pull this out, I'm left with an x plus 2. I'm left with an x plus 2. So we notice that if I distribute both of these terms into the same binomial, then that means both of these terms, get the right color here, plus 5, must be right up against the same binomial. And the only way we can do that is by putting the two factors side by side like that. There we go. Let's do one more with the leading coefficient. Instead of a positive 2, let's do a negative something. So a negative 1. Now, again, one way to do this, and many people show, is to factor out that negative right from the start. I'm not going to show that way strictly because what I notice a lot of students do is they'll factor out a negative 1, they'll change all their signs, and they'll do an excellent job and reach a number, and that negative factor never works its way down. So I'm going to show you a slightly different way that keeps the negative in till the end, and then we'll pull it out. So that way you don't forget about the negative. So I'm going to take my first term and my last term, multiply them together, I get a positive 15. List my factors of 15, which are 1 and 15, and 3 and 5. And then after that, I've completed the loop. I notice that because they're positive, I'm summing them. I get 16, and I get 8. I'm looking for a 16, so I know how I'm going to split it. Negative y squared minus 15. I'm going to go ahead and subtract a 1y and subtract a 15y. Do you notice how this time I'm making a negative? Even though I'm summing these, I put negative signs in front of both of them. Because albeit if I plus plus, that would make a positive 16. We would be able to get an answer, but it wouldn't, if I redistributed this, refoiled this, and I didn't include that correct signage, this wouldn't lead to my original question. So again, if I picked the 3 and the 5, I would get an answer, but it wouldn't foil to my original question. We'll see what that looks like at the end of this. So let's take a look. Now again, remember, we're leaving the negative in until the end. But there's no reason that I can't pull out a negative y, and a negative 15 is my two GCFs. So I'm left with a y plus 1, and I'm left with a y plus 1. And again, just to reiterate, the only way that these both can get distributed into the same thing is if they're both against the same binomial. Now normally we would box this up here, but oftentimes, many courses, we don't like a negative leading coefficient. So what we'll do is we'll actually factor out an additional -1, I'm going to show that right here, out of this factor. So that would mean that becomes a positive y and a positive 15. And the reason why we do that is so that we always have positive leading coefficients. Because if I have the negative here, it works. And if I take that negative and put it here, I would have a negative y minus 1 and a y plus 15 over here. And they would look like different answers, but in reality, they're both the same answers. They both have a -1 common factor that we have to deal with. So let's go ahead and knock out this last one. Now we're going to do this last one 2 different ways because many of you might be asking, well, what if I pick the wrong factors? Would I notice? And most of the time, probably not, but let's check it out. So I'm going to take -4, positive 20, multiply them together to get -80. List my factors. And once I complete the loop, add them all together. Well, actually, no, and this time I'm going to take the difference because I have a -80. So 79, 38, 16, 11, and 2. I know I'm looking for an 11, which means I'm going to take that -4x squared plus 20. I'm going to split it into a positive 16 and a -5, which I know combined to get me that 11. And when I factor this, I pull out my GCFs of -4x, -5, -4x minus 5. I notice that they're both, when I factor them out, they both must have been distributed into an x minus 4, which means the only way they could both be distributed into this x minus 4 is if they're both right here, which would mean that once I factor out that -1, 4x plus 5, and x minus 4, and I pull the -1 out right here at the very end. Now again, oftentimes you'll see teachers pull it out right here, but I find that it doesn't travel well with a lot of students. They'll forget about it up here and say, oh, I forgot to drag that all the way down. So I like to do it at the very end. That way we know for sure we didn't forget it. Now, the last question is, what happens if I pick a different set? What happens if I don't pick the 5 and the 16? Will it work with the 4 and the 20? Well, yes, it will, but we'll notice that they don't make an 11. Let's say we don't notice that. Let's say I pick my -4x squared, and I do, let's see, minus 4x plus 20. X plus 20. Will that still factor and get me an answer? Well, the short answer is yes. Remember, we're not doing number 10 here. We're actually just reworking number 9 and seeing if we can get the same thing. Now, I'm going to pull out a -4x. I'm going to pull out positive 20. 4x, 20. I notice that, okay, that's an x plus 1. That's an x plus 1. Hey, I have an x plus 1. I have a -4x plus 20. I have an x plus 1 and a -4x plus 20. And even if I factor out the negative, I have an x plus 1 and an 4x minus 20 with a -1. Again, I could pull out a 4. It's a negative 4. X plus 1, x minus 5. And we notice those aren't the same things. And you're like, well, what makes this answer any different than that answer? And the key is this should FOIL or redistribute back to our original question, because remember, we're undoing the FOILing process. So if I actually work this out, I'll get this. Let's double check to see if I work that out, will I get my original question? So I'm going to check it. Let's distribute the 4x. Let's see, 4x squared minus 16x. Distribute the 5 plus 5x minus 20. Still have my negative 1. That is a 4x squared minus 11x minus 20. Distribute that negative 1 in there. Negative 4x squared plus 11x plus 20. And that actually is our original question. That doesn't happen when I do this. If I distribute my x, negative 4, I get an x squared minus 5x. Distribute my 1 plus x minus 5. Then if I negative 4, x squared minus 4x minus 5, which becomes a negative 4x squared plus 16x plus 20. We notice this is not the original question we started with. So I know that this does not work. This is the only one that does.